Hey guys, so let's continue with chapter 4. Sorry, this supplementary lecture is a little bit late this week. I'll be putting this up on Friday, and straight away we'll have actual Friday's lecture as well. So we're talking about our Lewis structures and the shapes of the molecules based on how those molecules try and get those bonding pairs and lone pairs of electrons as far away from each other as possible, maximizing bond angle to minimize repulsion. Negatively charged pairs of electrons repel other negatively charged pairs of electrons. Now we focus mainly on molecules with just one central atom, but of course realize that many molecules have a backbone of atoms to create much bigger molecules. A good example of that is just looking at aspirin, which of course kills pain, helps with a fever, and is also anti-inflammatory if you have some kind of sports injury, or any injury for that matter. It can dissolve and get into the bloodstream in about 20 minutes. However, when we look at the aspirin, this is not the active form of the drug. The active form is actually the salicylic acid on the left here. But the problem with the salicylic acid is that it has these very potent oxygen to hydrogen bonds, which are acidic bonds and therefore are easily broken, giving us these acidic hydrogens. This is the whole basis of acidity in acid-base chemistry. These bonds, which are easily broken, release hydrogen. That's the job of an acid according to the Bronsted-Lowry theory, a hydrogen ion donator, or a proton donator as it's sometimes known. So we have to mask that acidity by adding on this protecting group here, CH3CO, and it drops the acidity down, and so you can take the aspirin orally. If you didn't have that protecting group, the salicylic acid would be too caustic and it would burn up in your throat, probably make it very difficult to breathe. So we mask that acidity, but then in the bloodstream, of course, there's lots of water in the bloodstream, and so that protective group is removed by water in hydrolysis actions to give the salicylic acid the active form once it's in your bloodstream. You can see the two molecules are made up with a whole contortion of atoms together. We've got 1, 2, 3 bonds around carbons to make these trigonal planar shapes. We've got 2 bonds and 2 lone pairs around the oxygen to make the non-linear shape. 1, 2, 3, 4 bonds around the head of that protecting group to give us tetrahedral. So molecules are often combinations of shapes, and to designate shape we have to look at one single point in space and look at the electrons around that specific point. Keep in mind that there are also drawbacks to using aspirin. It thins blood platelets, which is going to be a big problem for people who are anemic. But it can also be a help, because if you have a patient you suspect is having a heart attack and he was conscious, you'd probably get him to chew in a couple of aspirin to help thin the blood and make it easier for the heart to pump the blood around the body. Do keep in mind though that aspirin is caustic, or has that caustic nature. It can sometimes lead to gastric bleeding. Therefore, some people will take a break between using aspirin for headaches and fevers and switch to something else like acetaminophen after maybe 6 months at a time. So 6 months aspirin, 6 months acetaminophen, 6 months going back to using aspirin. And you can see with the acetaminophen, it's a big jigsaw puzzle of pieces in the molecule as well. You've got 3 bonds and a lone pair, trigonal pyramidal, 3 bonds to make trigonal planar. It's a good contrast between these two shapes. People often get them mixed up. Remember, trigonal planar does not have lone pairs. 2 bonds and 2 lone pairs, of course non-linear. 1, 2, 3, 4 chemical bonds back to tetrahedral. Now, acetaminophen is good for pain killing and reduces fevers as well, like aspirin, but it does not have any anti-inflammatory properties. It's not going to help with swelling from some injury. Of course, if it's giving you pain, you could certainly take it for that. But the big problem with acetaminophen is that it's poisonous to the kidney and liver. The CDC recommends a strict limit of about 4 grams of acetaminophen per day. And the CDC reckoned about 5 years ago that somewhere between 150 to 200 Americans die every year from an overdose of acetaminophen. Now, sometimes tragically, that's because people are deliberately taking an overdose. And sometimes people don't realize they're taking an overdose because they might be taking some kind of remedy for flu, which has acetaminophen in it, while also taking acetaminophen or something like Tylenol, which is more about maybe a headache they've got along with their flu. And so they could be unwittingly taking larger doses of acetaminophen and then overdosing over the course of a couple of days. Again, lots of shapes, lots of combinations of bonding pairs and lone pairs as we look around these bigger molecules. Now, the last major piece of work we have for chapter 4 is looking at polarity in molecules. This just simply means that we have molecules which have a majority of electrons on one side of the molecule compared to the other. So the side of the molecule which is electron enriched would be negatively charged, and the side of the molecule which is electron deficient would be positively charged. Poles of opposite. And so these charges we find in molecules, these polar molecules, can lead to changes in physical and chemical properties, so they are important. So how does this happen? Because we had said that covalent bonds were when the atoms were sharing electrons. Of course, we know about the trends in the periodic table as we move from left to right across the period, across the row. We're talking about the same row, so we're talking about the same number of shells, but the number of protons increase. And so atoms with more protons are better at attracting electrons from other atoms. We look at elements in the same group up and down the table. Try and get this all on here. Looking across that group. So up and down. So one sec, let me just see. Yes, hang on. Okay, crisis avoided. She didn't like the bread in her turkey sandwich, and she's going to eat it for a Twizzler. Right, so as we look at the elements within the same group, because that's moving down the rows, as we look at that particular column, as we move down through the rows, we're adding shells of electrons. So as we move up the group and we remove those rows, those periods, we're getting elements and atoms with fewer shells. And so the electrons are physically closer to the nucleus. And that also leads to a stronger attraction for electrons. We can see that if we look at a periodic table with electronegativities. That trend, 0.9 for sodium on the left, it finishes at 3.0 with chlorine on the right, 2.5 for iodine at the bottom, or as far as it goes here, 4.0 for fluorine at the top of that group. So again, let's see, my annotation across again. So moving up the group, hey, not the best line I've ever drawn, nor is that, but never mind. Moving up the group, it's about the removing of shells. Daddy? One sec, sweetie, excuse me. Right, so moving up the group, we're stripping away shells. And so those electrons, even electrons in other atoms, are physically closer to the nucleus. So there's a stronger attraction. As we move from left to right, we're seeing stronger attraction because the atoms on the right have got more protons. Electrons are attracted to positively charged protons. So those electrons being shared are not always being shared evenly. And that's what creates the polarity. So we take a look at some examples. So you'd always again be given a table of electronegativities in an exam. And as we compare atoms which are chemically bonded to each other and compare and contrast the difference in electronegativities, the covalent bonds that we've been talking about give us differences in electronegativities which are less than 0.5. Carbon to hydrogen, 2.5 for carbon, 2.1 for hydrogen, so a difference of just 0.4. Sulfur to carbon, 2.5 to 2.5, so a difference of 0. Boron to phosphorus, 2.0 to 2.1, so a difference of 0.1. And phosphorus to hydrogen, no difference. So these bonds are truly covalent bonds because the atoms are evenly matched in their ability to attract electrons. They are sharing those electrons. Of course, in chapter 3, we saw in ion chemistry, when we joined metals and non-metals, they were not sharing electrons. They were not equally matched. They were actually stealing electrons from each other. The non-metals, with the higher electronegativities, stealing electrons away from the metal. And we saw these huge differences in electronegativities, and normally greater than 1.9. And so when you look at the elements and look at the electronegativities for elements in a chemical bond, if the difference is greater than 1.9, it's normally an ionic bond. But that gives us a middle ground that we haven't talked about, where the electronegativity difference could be 0.5 up to the 1.9. That's the range for our polar covalent bonds. So the atoms are sharing electrons, but they're not sharing them evenly or fairly. One of the two atoms has a larger slice of the electron concentration or density. A little bit like sharing a cupcake with a sibling, maybe a younger sister or something, and you give them just a tiny corner of that cupcake. You can technically tell your parents that you shared it with your sister, but your sister probably doesn't feel like she got a fair share. You got the larger slice of the pie or cupcake. And that's what these atoms are experiencing with these polar covalent bonds. One of the two atoms, the more electronegative, has the advantage, but it isn't able to drive home that advantage and steal the electrons. The other atom is still hanging on to a slice of that electron density. So hydrogen to chlorine, a good example, 2.1 for hydrogen, 3.0 for the chlorine. So with a difference of 0.9, that is now considered to be significant, and we say that the bond is polar. We draw alongside the bond in the Lewis structure, we draw this dipole arrow with a little check close to the end of the other side because it makes it look like a plus symbol. That's of course on the side of the less electronegative element. That's the element which is having electrons withdrawn away from it, so it makes it feel electron deficient. We signify that with that little delta plus symbol. The electrons, meanwhile, driven towards the chlorine because of its greater electronegativity, its greater attraction for electrons. We put a little delta negative next to the chlorine atom. that dipole bond always points, that dipole arrow rather, always points to the more electronegative element. It's like you asked where the electrons are heading. They're heading that way. They're heading that way. It's almost like you've got a bathtub and you tip the bathtub up at one end and most of the water runs to one end of the bathtub. So one end of the bath is kind of electron deficient or a shallow end, and then one end of the bathtub is water enriched or electron enriched. And that's all we mean when we say that a bond is polar. Most of the electrons are skewed to one end of the bond, closer to one of the two atom nuclei. So we're always looking for that range of 0.5 up to, 0.5 up to 1.9. Anything less than 0.5 is going to be covalent. Anything greater than 1.9 is going to be ionic. Now the exact line in the sand is sometimes a little bit blurred, but that's usually the range we use for deciding whether the bond is covalent or polar covalent or ionic. Inclusive range of 0.5 up to 1.9 for a polar covalent bond. Okay. There we go. Couldn't get it to come off there. So polar covalent bonds, sometimes called dipole bonds. One of the two atoms is much better at drawing the electrons towards it, and so the wealth of the electrons are focused towards that atom. And the less electronegative element has just a small slice of that electron pie. With our next video coming out shortly today, we're looking at the polarity of the entire molecule. So not just individual bonds in the molecule, but the entire molecule. Sometimes molecules of polar bonds make the molecule polar. Sometimes those polar bonds cancel out. And we'll look at that and look at some specific examples as we finish off the chapter. Okay, stay safe, wash your hands, wear that mask.